Here we will see how to test complex experiments in quantitative trading using Python 3.8. We'll use Python 1.7 as our IDE running on Windows. Specifically, we'll discuss how to optimize a basic moving average crossover strategy. Very frequently, we hear financial specialists claiming that their strategies perform in some way, but the only close, but imperfect, way of assessing that is to test it using real data. We'll still have an issue. Past performance isn't a guarantee of future returns, so even if a strategy does look good on past data, it could be terribly bad using future or even current data. Disclosure: this exercise is shown for educational purposes on Python programming and should not be used for real financial purposes. Nothing in here constitutes any financial advice nor trading recommendation. Always speak to your financial advisor. In order to download this project, you need to visit this GitHub link over here and download the sample project. Additionally, you need to install Python from www.python.com and configure Python in there. We could naturally use other IDEs such as Spider or Jupyter Notebooks, but they are not designed for complex and messy experimentation like the one we're going to be using here. You can just go to File, then click on Open and choose the project you just downloaded. The minimap on the upper right part of the screen will allow us to easily navigate through the project. This programming environment works by adding panels, which we can add by pressing F2, and then connecting these panels using connectors, which can be added by pressing F3, into the in or out parts. It will allow us to see all of our results within the same screen, and is really meant for experimentation and data science testing. Also, it will be great for organizing your project in a nice and visual way. The markers, shown on the lower left part of the screen, can be used to easily navigate through your project just by clicking on them. There are several quantitative trading modules for Python. Backtesting is one of the easiest ones to use. In the top panel, we will import the necessary modules. In particular, we will import the backtesting module, which is going to be the cornerstone of our testing. We will use Yahoo Finance to import the stock prices. We're going to add 5 panels that will consume the code from the upper panel, one for each big tech company: Google, Microsoft, Apple, Facebook, and Amazon. The code will be the same, so let's have a look at Google prices. We will load daily prices from 2015 to 2020, and we'll keep the open, high, low, and close prices. In order to use backtesting, we need to wrap our code inside a class, which we'll name SMA Cross. It will have 2 moving averages. The first one will use a smaller window, and the second one will have a larger one. The idea is the following: if the first moving average, in our case MA1, is below the second one and crosses it by going up, then we buy the stock. On the other hand, if the first moving average is above the second one and crosses it by heading below, we sell or short the stock. In order to run this, we call the backtest function, and we pass that class that we defined. If we click on Run Below, all the panels that are connected to the Out button here will be executed. Hooray! This means we can run whole sections of our project with just one click. After a few minutes, we get the results that we wanted. First, notice that the data frames generated or modified in each panel appear next to them, and the same happens to the plots. If we look at the returns across the different stocks, we can see that they generally perform quite badly. Let's have a look at Google. We got a minus 50% return, meaning that we lost $5,000 given that we started with 10,000. That looks even worse when we compare the performance to the buy and hold part. We would have made a 180% return. On top of that, we just have a 32% win rate and a max drawdown of 61%, meaning that in the worst part of the simulation, we were 60% down. Almost seems that it can't get any worse, can it? For Amazon, we did something extra. Because we did reasonably well with a 50% return, we carried 3 sub-experiments with different parameters for the moving averages. We also added a frame by pressing F5 to group the 3 experiments together. The results are not that different. We also added an extra panel using matplotlib, where we want to see how the stock price evolved. Plots appear in Python next to the panel that created them. For Apple, we got something promising in principle, a 89% return, but with a very weak Sharpe and Sortino ratio. Remember that for sharp, we usually want something above 1, and for Sortino, we want something above 2.2. That's not close to being a solid strategy, but at least it gives us something to work with. Let's assume that we continue with it. One thing we want to do is test how it works with other periods. A good strategy should behave similarly across different periods. What we want to avoid is having a strategy that has extremely good results for a small amount of time and behaves badly for the rest of the time. The reason is that the strategy could be bad, but just because of luck during a very limited amount of time, it could appear to be good instead. Here, we are splitting the data frame into two parts, using the pandas.head and pandas.tail functions. And we are also printing a histogram of the prices. As we can see, the prices during these two periods are very different, yet the strategy works fine, and is similar across both periods. This is a good indication that the strategy is robust, but we probably would like to do further testing still. Of course, we could add more panels and run this again. Let's see how to do that. We add a panel by pressing F2, and then add a connector by pressing F3. Now we can run this again, but only the panels connected to it as input. This avoids the necessity to recalculate all of the other panels. If you want to avoid creating extra panels, we can also freeze the current results and run again after we change the code. In this case, for example, we change the dates. We can compare the current outputs versus what we had before. Since Apple looked promising, we'll do a formal optimization by choosing the best parameters for the moving averages. Python will allow us to separate different functional areas of our project and run them individually. Here we are placing the optimization part in a separate area. Note that the backtesting module has an optimization function, but we will use an external one that gives us more control over what we're doing. We will use the genetic algorithm module. We won't review how it works here, but you can check its documentation. Long story short, it will allow us to optimize functions with more flexibility than traditional optimization algorithms such as gradient descent. We need to specify a function to be minimized. In our case, we'll call it f. This f function will return the best pair of values that minimize our target function. Since it will be minimized, we are returning the negative value of the strategy outcome, meaning that, for example, a strategy where we end up with 20,000 return will return minus 20,000 here. The if statement, if n2 is greater than n1, is used to ensure that the second moving average has a bigger window than the first one. In case that doesn't occur, we return a large positive number. The boundaries that we will pass here will be 0 and 50 for each parameter, and we are also telling the algorithm that we want to treat each parameter as integers. After a long time waiting, we will get the best solution parameters and the objective function result. Because this optimization algorithm is stochastic, you will get different results every time you run it. But in general, you'll get a result of around $42,000 as the final outcome with the two parameters near 3 and 19. Pay attention here. This genetic algorithm module creates a window showing the convergence of the algorithm. We need to close it in order to allow Python to continue. Overall, this looks much better than the previous Apple example without any optimization. We're almost there. Let's rerun the same process now using these parameters, and we get a spectacular 327% return, which demolishes the 216% buy and hold return. The sharp is now 1.1 and Sortino 2.3, which makes this a good strategy in principle. All the rest looks solid. A max drawdown of 17 is acceptable, and an average return of 2.20% per trade looks good as well. The final question is whether this strategy is really robust or just a result of overfitting. Maybe because we optimized too much, we got a good result which will not hold in real life. In other words, we may have been optimizing to a point where we are making profits due to the noise in the data and not the real structure in there. What we can do to check that is to do subtests in small time periods and check if the strategy behaves similarly. Another strategy, which would be much better, would be to have a testing dataset which we haven't used to optimize and see if we get good results there. Anyway, going back to our original plan, we carry 4 experiments and see how this strategy works in 4 separate years. Many of the metrics in general, and the returns in particular look quite similar across the 4 different years. Further testing is necessary, specifically with the data we haven't seen, and even so, we really never know, because past performance is no indication of future returns.